All right, we've looked at least squares problems in the past. We're going to look at them again a little bit. So again, why is it called least squares? We're basically minimizing this quantity, ax minus b. So if we think of the error as being the difference between ax and b, and so the individual elements of that error then basically are this way, then the norm squared is equal to the norm of ax minus b squared is equal to the norm of the error squared, which is the error transpose times the error, which is the sum of the squares of the elements of the error. Okay, so we're minimizing the sum of the squares of the error, so that's why it's called least squares. Now, there's more than one kind of least squares, and so I'm going to talk about that here. So there's what's called the ordinary least squares. So sometimes we'll just see it as LS, abbreviated, or sometimes we'll see it as OLS, ordinary least squares. So in an experiment, we set x and we would measure y, for example. Since the x was set, there's no error associated with it, while y could have noise associated with it. And so when we set up the parametrization, this is what we had. The y was the noisy part, x was assumed to be exact, and p what was desired. So we had noise, uncertainty, but it only appeared in this term here. Okay, so we're going to move on now to talk about something called the total least squares problem. In another experiment, we measure both x and y. And since x and y are both measured, they both have noise. So y is noisy, x is noisy. And so the question is, how does the fact that x is now noisy, how does that affect the solution? And it does affect the solution. It can have profound effect on the solution. Okay, so basically, if we think of the linear problem of finding x for this hypothesis, so it's not, so y is equal to ax, okay? The total least squares problem can be written this way. It can be written as the minimum over delta and e, such that we're looking at the sum of the squares of the elements of delta, sum of the squares of the elements of e. And so we can think of it this way, as the minimum over delta and e of the Frobenius norm of delta and e. Okay, so we can think of actually e as being the measurement noise in y, and delta being the measurement noise in x. But here we can now write delta and e and put them together and call that delta hat. A hat we can say is a and minus y, and x hat is x and 1. And so this equation can be written this way. A hat plus delta hat, so this plus this times x hat is equal to 0. So notice this is a null space calculation. So that's what this is. So in terms of computing minimums, one way we can do this is to do a singular value decomposition. And we can go through and show that the smallest delta that makes this 0 is what we're looking for. Okay, and so I form a dyad from the smallest singular value, and so I can go through and show that in fact that is the delta that is the smallest, and so we can go through and show that the Frobenius norm of that delta hat is smaller than any other delta hat in Frobenius norm. So that's one way of looking at this total least squares problem. Another way of looking at the least squares problem is again looking at just the basic linear algebra problem. And so the question is, what's the difference between the LS, or ordinary least squares? In that case, only the b is uncertain in the ordinary least squares problem. In the total least squares problem, both a and b are uncertain. So that's one of the differences. Now in the ordinary least squares, for this line, y is equal to mx plus b, we have the error y is equal to minus mx, or y minus mx minus b. Okay, so the error can be written this way, y minus xp. And we've seen that the least square solution is the pseudo-inverse of x times y. Pseudo-inverse of y, of x, we can kind of think of that as dividing. It's not exactly dividing, but it's kind of like dividing by x. But in this case, in the ordinary least squares problem, this is known. So we're dividing by something that's known. Okay, so in the total least squares problem, now this quantity is unknown. So we can think of it y is equal to mx plus b, but we have both errors in y and in x. So y minus e, mx minus w. So e and w are both uncertainties, and And so we're actually trying to solve this problem. So these are unknown, and we're trying to solve for these guys. Now, in the least squares problem, since only the y values are in error, the ordinary least squares approach minimizes the error only associated with y. So the distance from the line to the points is what's minimized. Okay, so it's only minimizing that vertical direction. The vertical shift is what it's trying to minimize. So that's basically what's happening. With the total least squares problem, we're actually trying to minimize the distance from the points to the line itself. So that's not just the vertical, it's also the horizontal. And so we actually get these diagonal types of distances that we're trying to minimize. Okay, since errors can occur in both x and y, the total least squares minimizes the distance from those points to the line. So in a particular problem with a particular data set, the two are going to be similar to one another. The total least squares and the ordinary least squares are very similar to each other, but you can see they're going to give slightly different results. Okay, so sometimes one is going to be superior to another, depending on the problem and the data and so forth. So they give slightly different results, and it's nice to have options to work with. So now with the total least squares, we can actually do stuff that we can't do with the ordinary least squares, which is another advantage. So instead of parametrizing the line this way, this is a common way of parametrizing a line. Y is equal to mx plus b because we have slope and intercept. Instead, we're going to parametrize the line this way. A plus r1x plus r2y is equal to 0. Okay, and we're going to say that r is equal to r1 squared plus r2 squared and set that equal to 1. Okay, so this is a little bit different. We could say, for example, that r1 is equal to sine of theta, r2 is equal to cosine of theta, and so we can say this in general for the angle theta. So that would be one way of making sure that this is the case, and so then we would vary theta in all of this. The reason why we would choose to parametrize the line this way is because either r1 or r2 could be 0. Okay, so in particular, if r2 is 0, that basically corresponds to having a vertical line. There's no reason why you couldn't have data that gives you a vertical line. And so in the standard, the ordinary least squares, if we parameterize this way, that corresponds to having a slope of infinity, which is not reasonable. Okay, that's not reasonable. But we can still have a line that is vertical. So the challenge here is that when you have a vertical line, that basically corresponds to something that's not really a function. Okay, it's not really a function, and so that's why it's often not looked at. But it's possible for you to actually have data that fit that line. Okay, so the value of this total least squares regression approach is that we can still work with it. Okay, so in the total least squares regression, we're going to define these variables x and y and r as r1 and r2. And we're going to define mean values of the data. So we have the data in x, the data in y. X bar is the average value of the x values. Y bar is the average value of the y values. And z bar is x and y bar put into a vector. Okay. You can go through and show that x bar lies on the line of best fit. Actually, that it lies on the line of best fit for both ordinary least squares and total least squares. So we can show that it needs to satisfy this. And so basically, if we know r, we can go through and find a from this expression. Okay. So the line now can be described by its error. So the error is equal to a plus r transpose z, which is, so if a we get from this expression, then this we can actually write out this way. R transpose z minus z bar. Okay, and again, we want that to be small, or we want to set it equal to 0. So that's the kind of thing we're looking for. And so the total least squares cost is we're minimizing with respect to r and z of this quantity, where r satisfies this condition. Okay, so that's actually what we're looking for. So we can go ahead and put the data, stack the data together. So here is r1 times Z1, R2 times Z2, that quantity squared. And that quantity squared can be, the sum can be written as this matrix product. This times that times that. So notice that this is the transpose of this. That is the transpose of this. So we actually have this expression, which is basically the 2 norm of BR, where B is this quantity, squared. And it's subject to the condition that the 2 elements, the sum of the squares of them is equal to 1. And so we have this problem. The total least squares problem boils down to this. So we're trying to minimize this cost function subject to the norm of R equal 1. And so you can go through and show that the solution to this minimization problem is the singular vector associated with the minimum singular value of B. Okay, so if we take the singular value decomposition of B and we form, so the V here is the right singular vector, we're going to take vector 2 as R. Okay, and so from this then we have that the slope is given by R1 minus R1 over R2, and the intercept, if R2 is not 0, is, so obviously if R2 is equal to 0, this is not going to work. We basically get infinite slope in that case. And so this is the intercept that we get. So notice it's a function of the average values of x and y. So here's the slope that we get, and here's the intercept. So we have an approach for solving the total least squares regression problem. So in summary, for an additive perturbation, we have this result. It involves the smallest singular value. For a multiplicative perturbation, we have 1 over the largest singular value. All right, what about the Frobenius norm minimization? Suppose we have this problem. We have this matrix, and we want to minimize this quantity, A minus C times W. So we're going to minimize over C and W, subject to the fact that C is some complex value, and W is a complex matrix that's unitary. Okay, so in this quantity, we're looking for not just any W, we're actually looking for a unitary W. We want to find a matrix that is a constant times a unitary matrix that is as close to A as possible in the Frobenius norm. So this is just another minimization problem. This minimization problem also arises in some practical applications. Now, in working with this F norm, the Frobenius norm minimization, we can define this inner product, the inner product between matrices, x and y, as the trace of x adjoint y. Okay, and so again, this is, when you take the trace, you're getting just a scalar value. And we can go through and show that this, for matrices, this satisfies all the properties of the inner product. So we can go through and show, and I have the proofs, you can see the proofs video to see this, that the solution to this minimization problem is that W is equal to the this product of the singular values of A, the singular value decomposition, the unitary matrices of that. Notice that this product of unitary matrices is itself a unitary matrix, and so and the C, the constant, is 1 over n times the inner product that we just defined times of W times A, which we can go through and show is 1 over n and times the sum of the singular values. Okay, so this then is the solution to that Frobenius norm minimization problem. So here we have some least squares types of problems that we can actually solve and get some mileage out of. So it's helpful to have these kinds of tools available for us, and we will come back and use these tools later in various applications. So stay tuned for the practice problems and the proofs.